Today what we're going to look at is an RTD. This here that I've got in my hand is an RTD, resistance temperature device. It detects temperature by change of resistance. And what we're looking at here is it's a metal tube. Inside the metal tube is a wire wound resistor, very thin wire made up of platinum. Now an RTD can be made up of other metals like nickel and copper, but the most common is a platinum RTD. Now platinum RTDs characteristically have 100 ohms resistance when they're exposed to a temperature of 0 degrees C. This here is a 3-wire RTD. It has 3 wires, and the reason for the 3 wires is when we're connecting it up to instruments, the instrument can compensate for lead wire resistance. That lead wire resistance, as you can see, we've got quite a lead here. That adds to the total resistance measured. But that resistance isn't a reflection of the temperature that this RTD is actually measuring. So what we're going to do is look at what each one of these wires are. And you can see 2 of them are the same color, black, and 1 of them is red. The black lead actually really goes out through the cable to the connection of the RTD and then comes back on the other lead. It really is just a wire that goes out and comes back. The red is attached to the RTD resistance on the inside. The other side of that resistance is connected to that point of those 2 blacks in here. So really what we have is we have one side of the resistor and the other side of the resistor. What we're going to do in order to take a direct measurement of temperature with an RTD, we're first going to measure the resistance of the leads. And the way we do that is we take our ohm meter, like we got here, wait for it to boot up, and what I'm measuring here is I've got my ohm meter connected between the 2 blacks. And what I'm measuring here, it says 3 ohms. So it's saying that the lead wire resistance is 3 ohms. Now, I've got the RTD sitting on the table. I'm going to just move my measurement right here. There we are. Now I'm between one of the blacks and the red. Okay, and what I see here is 111.4 ohm. I have to remember that 3 of those 111.4 ohm is actually just the leads itself. So let's see what this RTD is telling us. So the lead wire resistance was 3 ohm. Okay, and what I've got on my ohm meter there is 111.5 now.
Yep.
Okay, well it's jumping around, so 0.5. I'll take the middle. I'm just going to go with 0.4. For our calculation today, that'll be fine. So if I take my 3 ohm away from the 111.4 minus 3 equals 108.4 ohm. 108.4 ohm for the RTD. So that's the actual resistance of just the resistor in that protected tube of the RTD. Okay, so the equation to determine temperature is the resistance of the RTD, R minus R at 0, all over the multiplication of alpha, and alpha is the ratio of change of resistance per degree Celsius, per ohm of the RTD, times what the RO is, R at 0. So what we'll be doing is we'll take 108.4 minus 100 all over 0.00392, that's alpha. And alpha is particular the type of RTD. Copper RTDs are going to be different, nickel RTDs are going to be different. Even platinum, you can get European or American RTDs and they will have a different alpha. So knowing the alpha actually is very, very important when you're doing the calculations. For the purposes of what we're doing here in Sheridan, we're going to use the American RTD, which is the alpha is 0.00392. And I multiply that by 100, 100. What I get is, here to bed mass, what I come up with is 21.43 degrees. And if I look at my temperature controller here, what I have is 21 degrees, and that rounds it off. And what we have here is the same. And if we look at the thermostat on the wall, what we're seeing is 21 degrees. What we're going to do is we're going to show you a little experiment that we're going to do with the RTDs. This one here, what we've got is a temperature transmitter. I'm going to connect the temperature or the RTD into the temperature transmitter. Let me just, I'll make use of this other RTD that I've got here, since I borrowed quite a few. You have to make sure that when you're doing these experiments, not to handle the RTDs too much. You will cause a change in resistance by just hanging on to the RTD. So what we see here, we look at what we have is connected. We have the red and the black, and as you can see there's the ohm symbol. That means that the resistance is between the red and the black, and these two blacks are actually connected together up at the junction of the RTD where it's connected. They're both sides of the resistor, the black and the red. We have our voltmeter connected between the 0 and 5, output of the transmitter, and a common. So what we have for the output is 1 volt, okay, and if we adhere to our mathematics that we've been doing, process variable is equal to signal minus offset all over the span times the range plus the lower range value. Now we can eliminate some of the terms of this equation because we're really dealing with 0 to 5 transmitter, and we're dealing with a process that goes from 0 to 100. So it's very simple. We just take our signal of 1 volt over 5, span from 0 to 5, multiplied by our range. Well, the range of our transmitter here is 0 to 100. So the range is 100 degrees C, multiplied by 100. That comes out to, if I do the math here, I do 1 divided by 5 and multiply that by 100, and I come up with 20 degrees. Okay, for this portion of the lab, what we're going to do is investigate what happens with an RTD in colder temperatures.
Yeah, you know what, Scott? I think it's time for a break because we've been working hard for our students all day. I think it's time for a nice cold beverage. What do you think?
Yeah, okay, you know, I can go for that. That would be really nice. I'll just check my equipment here to make sure I've got everything that we need. When we continue on, transmitter. Yeah, I think we've got everything we need.
Did you want one of these two?
Yeah, that'd be great, if you don't mind.
Thanks. Scott?
Yeah? Yeah, what?
What the hell is going on here?
Well, I needed like a cold liquid in order to do this portion of the lab. What?
Well, all right, you got my attention. Let's go. Let's see what you have.
Okay, all right. All right. Well, let's have a look now. We'll see what we've got. What are we reading here? We're seeing a temperature drop.
I hope these students are appreciating this because let's see what we have.
They're great students. They're really good students.
They really are.
Yeah. All right. Okay, so what we have here, what are we doing? We're down to about, it's showing here on this controller, 8 degrees C. And what I've got here is 106.3. So what I'm going to do is do the calculation first. So I take 106.3. Now remember, we had 3 ohms in the leads. We have to remember to subtract that. So I put that 3 ohms up here, And what I've got to do, see, I'm making it nice big markers. 3 ohms, 106.3, and we're down to 105.9. What are we reading here? 7.
Yep.
I'm going to have to change this, or either that would be really quick. So I'm going to say 106. We're around 106. So I got to subtract 3 from that. That gives me 103. Correct? Okay, so in order to do the calculation with the resistance, we would go 103 minus 100 all over alpha times R0. So that's 0.00392 times 100. Like that. Okay, you've remembered to subtract that lead wire resistance. So if I do this calculation, that's going to be 3 divided by, I've got 7.6 degrees. And if I look here, I've got 7, okay, and we've got the correct temperature.
It's a pretty accurate reading.
Yeah, I believe that's rather accurate. 7.65 degrees. Okay, so let's have a look at what the transmitter is telling us. So I'm going to look at the transmitter here, and it's reading 0.3 volts DC. 0.3 volts DC. So if I do the calculations to check for determine process variable, that's 0.3 divided by 5 times the range, which is 100. So let me do that on the calculator. Equals, and what I've got here is 6. Now we're out by a little bit, but there could be many reasons for that. Again, we have not checked the calibration of our transmitter here. These can be a little bit out, and even the manufacturer allows for a offset that you can actually program into it if you're not reading the correct temperature. And we still are holding here at 105.8, so it is the temperature is changing quickly, and it causes also too a little bit of an error. All right, that's good.
So that's a great experiment, Scott. I think this is going to be your drink.
Okay.
Bottoms up.
Cheers. Now make it a control. Oh, yeah, it's been a long night.
Scott, we've been going at this all day today. Did you want a tea by chance?
Yeah, that'd be great. If you don't mind, I could use one. It'll keep me awake. You know, our students deserve me to be awake and actually present this material.
Well, they're the best.
Yeah,
so
they are.
I want to make sure they get the best.
They are the best. You bet. Yeah, they are. Our students are the best.
Okay, I'll be right back with a hot tea.
All right. Okay. Thanks.
Scott,
yes, Dave.
you
Yes.
at it again? What's going on here?
Maybe they jumped in there. Okay, well, I actually do need like a warm liquid or hot liquid in order to do the next part of the experiment. It was available. It was sitting right there.
All right, you have my attention. Let's see what you have.
Okay, all right. Well, let's look at what we got here. What's our temperature controller reading right now?
80 degrees.
Oh, I got 80 degrees. Yeah, 80
81.
went up to 81. Okay, so what I'm going to do here, I'm going to put my ohm meter across the RTD, and it's looks like it's stabilizing at 134.
0.6, and we got 82 degrees here.
Yeah, 134.6, 134.6 ohms. There we are, 134.6 ohms. We have to remember to subtract the lead wire resistance. If you don't, your calculations come out wrong. So that's going to be 134.6 minus 3, which is 131.6. And that's going to be our RTD resistance. And I got to remember to put the ohm symbol in there. RTD resistance. Okay, so let's do the calculation. of 131.6 minus 100 all over alpha. RO alpha is 0.00392 times 100. And if I do that calculation, it comes out to 80.6. And it's really what we have been reading here. 80, 81. It did actually go up to 81. All right, so let's have a look and see what our transmitter is telling us. Our transmitter right now is reading 4 volts. 4 volts. So if I do process variable is equal to times 100 equals 80 degrees. So it looks like as the temperature goes up, our transmitter and our RTD resistance and our controller here, our Omron controller, are getting more in line. And what we Okay, so what we've seen here is we've done a direct measurement of the RTD resistance, remembering to subtract lead resistance. When they're connected into a controller or a transmitter, that is done by the electronics inside. The RTD is part of a Wheatstone bridge, and that Wheatstone bridge is a balance circuit. What happens is each one of those black wires is in the legs of, or in the opposing legs of the balance circuit. It's very similar to if I have a scale where I'm trying to measure the weight of something. If I put a weight here and another weight here, they'll balance out. If I put something in with that weight, it'll actually offset the balance. And that's what we're measuring, is that weight that we're adding to it. RTDs, resistance temperature detector devices, are in fact very accurate for their range of measurement. Okay, so what we're going to do is we're going to show you how we're going to determine the temperature of an RTD, or the temperature measured by an RTD, through a resistance table. Now, the resistance table is done by actual scientific measurement, so it is accurate, very accurate. The calculation actually is an estimation. So you have to know that the chart is a very accurate document, but we don't normally walk around with our RTD chart in our pocket, so if we can do the calculation, it makes it very easy to determine whether the RTD is okay. Dave, I didn't bring my RTD chart. Would you happen to have one around?
I actually have one in my pocket.
Oh, well, that's great. That's good. Thank you. Thank you. That's how about I happen to have oh yeah, you got a straight edge. Thank you.
Well, you've taken everything else from me. You may as well take that.
Well, yeah. So what we want to see here from this chart, along the top, it shows degrees C and ohms. Degrees C and ohms, right? So what we're doing, we're going to be looking to find our resistance measurement. So we looked at our cold beverage was actually 103 ohms when we subtracted the lead wire resistance. Our calculated temperature was 7.6. So what I'm going to do here, I'm going to look down the ohms until I come down to 103, which is right about there, right? It is 103 is just a little bit above, 103 would be right in between 102.78 and 103.18. So 7.5, 7.6, and what we had there is 7.6. So our calculation actually was pretty close, very, very close. Now if we look at the other one here, which is 108.4, we're looking down here till we get 108. There's 108.32, right? 108. Okay, 100 and where are we? 108.32 would be just past this. 21 degrees. They just passed 21 degrees. 21.4 is what we calculated, and this chart here being accurate, all right, at just a bit above 21 degrees would be our 108.4. Now the other one is 131.6. So we look down here and we look for the ohms at 131.6. There we are, right? 131.6. Somewhere right in in here, all right? And if we look at our temperature, 131.6 would be in between here. That's in between 80 and 81, and what we had is 80.6. So as we can see here, this chart is very accurate, and we can get the temperature we want from the chart. You have to remember always to subtract that lead wire resistance. The chart is the most accurate out of these two. However, you do have to extrapolate if you want to know the exact answer in between those. And we know that the transmitter can be used to transmit the signal. And we use a transmitter whenever the length of the RTD cable is far too long to be read by an instrument. We use a local transmitter to actually use a standard signal, converts the RTD measurement to a standard signal, and sends it off to our control system. All right, job well done. That was really good. Thank you, Dave. Thank you very much for your help.
Thank you, Scott. Thank you very much for your help.
I think it worked out well. I think our kids are going to get a lot out of it.
Yeah, well, they're the best, and they deserve the best.
Yes, yep, to our students.
Can you guys get out of my kitchen now? I have to start cooking.
Yeah.
Yeah.
Okay,
Okay,
we're out.